Hi, my name is Joseph Azevedo, and this is my lab report for Lab 1. In this report, I'm going to go over the purpose of the lab, the fundamental physics principles involved, the procedure involved and measurements taken, the computational model created to aid analysis, the overall results of the lab, during which I determined the charge of the 18 centimeter long charge tape to be around positive 8.5 nanocoulombs, and finally at the end I'll finish up with a few follow-up points. So starting off, the purpose of this lab was to explore the ways in which charged objects interact, and to use those observations to estimate the excess charge on charged pieces of clear tape. To do this, we're going to rely on a handful of fundamental physics principles, namely static electricity, the interaction of charged objects, the gravitational force, Newton's first and second laws of motion, the electric field and its resultant force, and Coulomb's law. The procedure itself was split into two main steps. The first step involved introducing the procedure of charging small pieces about 20 centimeters long of clear plastic tape by laying them down and rapidly peeling them off of a flat surface. This motion charges the loose tape, which we'll now refer to as U-tape, and this can be observed when you move your hand towards a loose piece of tape as it will be attracted. Next, I negatively charged a plastic pen by rubbing it against a dry cloth and then moved it close to a piece of previously prepared U-tape. When I did this, the pen and the piece of tape were attracted to each other. Because we know that like charges repel and opposite charges attract, we're able to conclude that the U-tape has a positive charge. Now that we know the sign of the charge, the second part of the procedure involves observing the forces that two pieces of U-tape apply on each other. I took two pieces of U-tape, A and B, and suspended tape B across a distance. Then I slowly moved tape A underneath tape B until I observed tape B beginning to float when they were about 1.9 centimeters apart. This is due to both pieces of U-tape having a positive charge, and since like charges repel, the electric force by tape A on tape B causes tape B to float. While doing this, I also measured the length of the floating part of tape B to be around 18.3 centimeters. Now that we've finished talking about the procedure, we can move on to the analysis, where I sought to estimate the magnitude of the charge on each piece of tape. To do this, I constructed a simplified model of the problem that involves a few key assumptions. Namely, first, that the charge of each piece of U-tape is identical and evenly distributed across its surface. Second, that because the charge is evenly distributed, we can instead model each piece of tape as a point charge. And third, we consider only the center of the tape that is floating, and we ignore any other forces, such as air resistance or tension. Given these assumptions, we can finally construct a model where tape B exists as a point charge that is positioned above tape A. Because tape B is stationary within our frame of reference, we know that the net force acting upon it must be zero, by Newton's first law of motion, and it is in equilibrium. By calculating the mass of the tape via its length and linear density lambda, we can use Newton's second law of motion and the acceleration due to gravity on the Earth's surface, g, to determine the magnitude of the force that tape B experiences due to gravity. Because the net force is zero, we know that the magnitude of the force on tape B created by the electric field for tape A must be equal to the magnitude of the gravitational force, and this lets us solve for the charge on each tape using Coulomb's law. This conceptual model was also created programmatically using GloScript. I'd like to take a second to walk through the major parts. First, I defined the physical constants and helper functions. Then, I added experimental measurements taken and code to visually display the experimental setup. Next, the most important part of the script is the actual implementation of the model, where I step through the calculation of each relevant physical quantity. Finally, I included some code to print the results out and create the force arrows. So, given this model, I was able to obtain the following results. The charge on each piece of tape using the idealized model was determined to be around 8.5 nanocoulombs, and this represents a net electron deficiency of around 53 billion electrons. By estimating the number of atoms on the sticky side of tape B to be around 347 quadrillion, this means that the tape had an overall electron deficiency ratio of around 1.5 hundred thousandths of a percent of an electron per atom. Now that I've discussed the results I obtained, I'd like to briefly discuss a few follow-up points. First, it is important to only ever touch the pieces of charged tape by their ends in order to maintain their charges on the pieces of tape. If we were to accidentally touch it somewhere else in the middle, we run the risk of discharging the excess charge present and ruining its use for the purposes of this experiment. I'd also like to consider for a second what would happen if protons were negatively charged and electrons were positively charged. In this experiment, we likely wouldn't even be able to directly observe any differences. The pen would instead be positively charged and the U-tape would be negatively charged, resulting in them being attracted just like before. In addition, the two pieces of U-tape in the second part of the procedure would remain repelled by each other, and our overall procedure would remain therefore unchanged. In conclusion, in this lab, we explored the ways in which charged objects interact, and we used those observations to estimate the excess charge on short pieces of clear U-tape to be around positive 8.5 nanocoulombs.